Hey guys, here we are, part 3 of our unit on covalent bonding. We're going to learn how to calculate the polarity of a covalent bond, and then we're going to talk about how to calculate if a molecule overall is polar or nonpolar. Okay, so probably the most important part of this whole unit here is understanding what polar and nonpolar even means. Polar bonds are when we have unequal sharing of electrons. That means one side of the bond has more electron density than the other. It's kind of like a tug of war. Nonpolar bonds are when we have equal sharing. Imagine having a tug of war with both sides are equally strong. So as far as atoms go, there would be an equal distribution across the entire bond. So just remember these two things as we talk about this today. We're going to use this chart on electronegativity to determine if bonds are polar or nonpolar. We talked about this before a couple months ago about electronegativity, and remember, electronegativity is the ability of an atom to attract electrons. So look over here, fluorine up in the right corner has an electronegativity value of 4. That's the highest one on the entire periodic table. That means fluorine wants electrons more than any other atom. Look at the bottom left, francium down there, 0.7. That means francium does not want electrons at all. It's more willing to give them away, which is what metals usually do. Notice how the metals on the left side of the periodic table have lower electronegativity values than the nonmetals on the upper right of the periodic table. Nonmetals want to attract electrons. We're going to use that chart to calculate the electronegativity differences between two atoms. One chemical bond, one covalent bond. So anything that has a difference of 0 to 0.4, that's going to be a nonpolar bond. Remember, nonpolar means equal sharing. So if their electronegativity differences are similar, they're not going to have unequal sharing. They're going to have equal sharing, and that's going to be nonpolar. Polar bonds will have a difference of 0.5 to 2.0, and ionic bonds will have a difference of 2.1 or above. So let's take a molecule like hydrogen fluoride. So we're going to take those electronegativity values from that chart and simply take the difference. So fluorine has a value of 4.0. Hydrogen has a value of 2.1. We subtract those numbers and we're going to get 1.9. And as you see, 1.9 falls into the polar range, so HF bonds are polar. So what this means is there's an unequal sharing of electrons. They're all going to be flowing towards the fluorine because fluorine is like an electron hog, has a really high electronegativity value. So most of the electrons are going to be near the fluorine, the electron density. I'm drawing little arrows here pointing to where the electrons are flowing. So what ends up happening, if you have more electrons towards the fluorine, it's going to end up causing a partial negative charge. It's a Greek D, it means partial. If you take calculus, they do a lot with that. So imagine all the electrons are kind of flowing up by the fluorine. The electron density is stronger over here. There's more electrons. So if there's more electrons on the fluorine side, that means on the hydrogen side, we're going to get a partial positive charge because it's now deficient of electrons. This creates something called a dipole, 2 poles. Just like the Earth has a north pole and a south pole, that's 2 poles. We could say the Earth has a dipole, but in this case, we're talking about molecules, and they're kind of like little magnets. So on one side, we'll have a negative charge. On the other side, we'll have a positive charge. Here's our dipole. We have 2 ends that have different charges. I'm sure you've seen bar magnets that are like this, where one side's negative, one side's positive. If we have this going on, this means we have a dipole. We have more electron density on one side of the atom as opposed to the other. Let's look at another example here. What if we have diatomic hydrogen? So if we did the electron structure for that, we would just have 2 H's next to each other. Okay, this would be a linear molecule. And let's subtract those numbers that we just looked at a second ago. Hydrogen has an electronegativity value of 2.1 minus another 2.1 because they're both the same element. We're going to get a difference of 0. Notice 0 is going to be nonpolar. This would be a nonpolar molecule. This means they have equal sharing of electrons. All the electron density is going to be equally shared. It's like having a tug of war with someone who's of equal strength with you. Neither is going to pull towards itself. You're going to have equal sharing. This is what nonpolar is about. So we have to take these differences here in electronegativity to calculate this. All right, let's look at another example. Here we have CH4, methane. So we're going to calculate the CH bond. Remember, we're just doing bonds right now, single bonds. All right, CHs. So we'll take the number for C, which is 2.5. If we look at our chart and we subtract the 2.1 from the hydrogen, we end up getting a difference of 0.4. And as you can see, 0.4 is nonpolar, so CH bonds are nonpolar. Because we have 4 of them, look, 1, 2, 3, 4, we could say we have 4 nonpolar bonds. And we have 0 polar bonds. So all you have to do is just count up how many there are. And since they're all CH, they're all the same, you don't have to do the calculation 4 times. You don't have to add them up or subtract them. Don't do any of that. We're just calculating the electronegativity difference of one bond, the CH. There just happens to be 4 of them. Okay, so here let's do carbon dioxide. Here's the structure for it. Here's the CO2. Okay, so we're just going to do the bonds here. So we have a CO bond. It doesn't matter that it's a double bond. All right, so it's just a CO bond. C's are 2.5. Oxygens are 3.5. If we look on the chart, we're going to take the difference. Okay, don't have negative numbers. These are always going to be absolute value numbers. We're just taking the difference. So this is going to be 1, not -1. No, there's no negatives up here. So take the positive number. So 1 is polar. Okay, so CO bonds are polar. How many do we have here? 1, 2. There's 2 polar bonds, not 4. Don't count the double bond as 2. It's just a bond between one atom and another. So doubles and triples, they all just count as one bond because we're bonding to another atom. So CO bonds are polar. We have 2 of them, one here, 2 polar bonds, 0 nonpolar bonds. Let's get back to talking about molecular polarity. The overall molecule, you have to figure out if it's polar or nonpolar. So again, we're going to draw arrows that move towards the atom that has a higher electronegativity number. If we looked at that chart, fluorine has a value of 4, hydrogen has a value of 2.1. So clearly the fluorine wants electrons more than the hydrogen. We're going by these numbers. So imagine the electron density moving this way by the arrows. Most of the electrons are going to be over here. We have our partial negative and our partial positive charge, and we create our magnet. We create our dipole. When this happens, this is overall a polar molecule. Polar means unequal sharing. This is unequal sharing overall on this molecule. We created the dipole. Whenever you create this dipole, you create a polar molecule. One side has to be negative, one side has to be positive. All right, let's look at these 2 molecules. One is linear. This CO2 is a linear molecule. It goes across in a straight line on the same plane. This water here is bent. Remember, these unshared electrons here are going to push these H's down and cause a bent molecule. So let's look at the dipoles on both of these. So first of all, our electronegativity values. Oxygen has a value of 3.5. Carbon has a value of 2.5. So the oxygens are going to be hogging the electrons. So they're going to be moving from this way over towards the oxygen, but also this way towards this oxygen. In this case, we end up having equal sharing. equal sharing. They're equally being forced onto the ends here, and because it's a linear molecule, imagine the tug of war going on where you have two guys on the ends who are of equal strength. You're going to end up having equal sharing. Equal sharing means nonpolar. So in this case, our overall molecule is nonpolar. Even though this number adds up to 1, we can still have polar bonds. Here we have two polar bonds, CO here, two polar bonds, but overall this molecule is nonpolar because it has to do with geometry. It's all about the geometry and the shape of the molecule. That's why we learned about them, one of the reasons. All right, how about water? Let's look at the water. Oxygen again has a electronegativity number of 3.5. Hydrogen is 2.1. Clearly, oxygen wants to attract electrons more than hydrogen. So let's draw our arrows. They're flowing up towards the oxygen, flowing up towards the oxygen. So here we're going to have our partial negative charge by the oxygen, and then down here these hydrogens are going to have a partial positive charge. Here's our dipole. We have the top being top being negative, the bottom being positive. Here's our pretend little magnet, and that's what water is. Water is a polar molecule for sure. We have two polar bonds. We take this difference, we're going to get 1.4. And overall, because of the shape. Over here, we would have electron density on the oxygens, partial negative, partial negative. See how this would be? You have negatives on each end. That's not a dipole. You have to have opposites on each end. That's what is the difference between nonpolar and polar overall. Let's look at another one. Here is carbon tetrafluoride. So we have a carbon in the middle, we have the 4 fluorines on the ends. So let's check to see if we have any polar bonds first. We have CF bonds. The numbers for these off our chart. Carbon's 2.5, fluorine is 4. Remember, we're taking the absolute value of these numbers, and we're going to get 1.5. 1.5 is polar. So we have 4 polar bonds. 1, 2, 3, 4, because they're hooked up to the carbon 4 times. 4 polar bonds. So now let's calculate if the overall molecule is polar. Which way are the electrons flowing? They're flowing to the atom with the highest electronegativity number, so that's going to be the fluorine. So they're going to be moving up this way. They're going to be moving all towards the fluorines. The fluorines are such electron hogs. It's not even funny. So there they go, all out to the fluorines. So our partial charges, our negative charges, are going to be by the fluorines. Imagine this in your head, what's going on. All the electron density is by the fluorines. Is this a dipole? Look, all the negative charges around the outside. Did we create our little magnet with one positive on one side and one on the other? No, we did not, because they're all being shared equally. This is equal sharing. Equal sharing is nonpolar. Nonpolar, equal sharing. Got to remember that. That's what makes this molecule overall nonpolar. All right, let's look at these examples. Here's our CF4. We already said this was nonpolar. So what if we have this, CFH3? So now what I did is I replaced 3 of the F's with H's. So now we only have 1 F. Okay, we only have the 1 F here. So which way is the electron density going to move? All the electrons, they're moving towards the fluorine. There's only 1 of them this time, so they're all going this way. Fluorine's going to try to take them away. It wants those electrons really bad. So we end up getting our partial negative charge on this side. The opposite side is going to be partially positive. I'll just write it in a couple times. You could just write it once to show that they're flowing that way. When we have unequal sharing, this is unequal sharing. They're all going to be over here. We're going to have our dipole on this side, negative here, positive here. There's our magnet. We have negative on one side, positive on the other. So this is a polar molecule overall. This is polar, unequal sharing. They're all on one side, not so much on the other. Let's take a look at these two examples here. So here we have SO3, and then here we have CH4. In this case, we have SO, which are polar bonds because it would be 3.5 minus 2.5, this equals 1. So we have 3 polar bonds here, 3 polar bonds right here. 1, 2, 3. Don't count this as 2. 1, 2, 3. So let's look at the overall geometry. They're moving towards the O's. There we go. All moving out. And because these are all the same atom, what do you think? Is this going to be unequal sharing or equal sharing? You got to think about the geometry. This is a trigonal planar. It's a flat molecule with all these O's on the same plane. We're going to have our electron density up here, our partial negative charges. In this case, this is equal sharing because these are all the same atoms on the end. Non-polar overall. So we can have polar bonds, but still have an overall non-polar molecule. How about this case? CH's 2.5 minus 2.1. So this is 0.4. So in this case, we have 4 nonpolar bonds. Okay, so if you have nonpolar bonds, they're all nonpolar, then automatically this is a nonpolar molecule overall. You can't have nonpolar bonds and then have a polar molecule. That can't happen. So if this is automatically nonpolar, if this is nonpolar, then this automatically has to be nonpolar. There's no even reason to think about it. You can think about it because there's equal sharing. There's no polar bonds. All these guys are sharing them equally. So here we go. There are 2 things that you have to consider if a molecule is going to be polar or not. First off, you have to have at least 1 polar bond. If you don't, then your molecule cannot be polar overall. You can stop right there. Secondly, the shape of the molecule. You have to look at it and consider the geometry and consider if one side is going to have more electrons than the other. You have to have that dipole going on where the electron density is greater on one side of the molecule or the other. And really, that's all there is to it.